Today, we're jumping into one of the most mind-bending puzzles in all of physics. It's a story about two twins, a really fast rocket ship, and a very, very strange truth about the fabric of time and space itself.
So, could a trip to the stars actually make you younger than someone you leave behind? I mean, that's the core of it, right? It's the famous twin paradox, and at first glance, it seems to create a massive contradiction in Einstein's theory of relativity.
So, here's the setup. Picture this. We've got identical twins. One of them, twin A, hops into a spaceship and zips off to a star 4 light-years away at a whopping 80% the speed of light. Twin B stays home on Earth. Now here's where it gets weird. From twin B's perspective on Earth, twin A is the one moving, so their clock should tick slower. But wait, from the traveler's point of view, it's Earth that's flying away from them, so the stay-at-home twins' clock should be the slow one. See the problem? They can't both be younger. So what gives?
And yet the physics, the math, it's totally clear on this. When twin A gets back, they've only aged 6 years. But back on Earth, 10 full years have passed for twin B. The space traveler is now 4 years younger than their twin. And I'm not talking about feeling younger, this is a real physical difference. So what happened to that perfect symmetry we were just talking about? What's the missing piece?
Okay, to figure this out, we need to rewind a bit. We've got to go back to the very foundation of Einstein's special relativity, which, believe it or not, is built on two surprisingly simple rules.
The first rule is pretty intuitive, right? It just says the laws of physics work the same for anybody moving at a steady speed, what physicists call an inertial frame. But that second rule, oh man, that's the real game changer. It says the speed of light is an absolute cosmic speed limit, and it's the same for everybody. This is where our everyday brains start to hurt a little.
Think about it like this. If you're in a car going 30 miles an hour and you throw a ball forward at 40, someone on the sidewalk sees that ball going 70 miles an hour. You just add the speeds. Easy. But light doesn't play by those rules. If you're in that car and you turn on your headlights, you, the person on the sidewalk, someone flying towards you in a rocket, everybody measures that light traveling at the exact same speed. Always.
So if the speed of light is this stubborn constant that refuses to change, then something else has to give. And you know what that something is? It's time itself. To really get this, we need another one of those brilliant thought experiments, the light clock.
Let's imagine the simplest clock we possibly can. It's just a single particle of light, a photon, bouncing perfectly between two mirrors. Each round trip, that's one tick of our clock.
Now, if you're right there with the clock, what do you see? The photon just goes straight up and straight down. Tick, tock. Super simple. We know the distance, we know the speed of light, so we know exactly how long each tick takes.
But what happens if we watch that same clock as it zips past us? Well, from our point of view, as it moves sideways, that photon still has to get from the bottom mirror to the top one. But because the top mirror is moving, the photon now has to travel a longer, diagonal path to catch up. It just has more space to cover.
And this right here, this is the aha moment. Remember rule number 2? The speed of light is constant. It can't speed up to cover that extra distance. So if the speed is the same but the distance is longer, what does that mean? The journey itself has to take more time. From where we're standing, the moving clock is literally ticking slower.
This mind-bending effect has a name. It's called time dilation. And it's not some kind of illusion. It's a real, fundamental property of our universe. The faster you move through space, the slower you move through time, at least compared to someone standing still.
Okay, so is this just some weird thought experiment, something that only exists on a blackboard? Nope, not at all. We have cold, hard proof hitting our planet every single second, thanks to something called cosmic rays.
So when these cosmic rays smash into our upper atmosphere, they create these tiny, unstable particles called muons. In a lab, these muons have a crazy short lifespan. We're talking just 2.2 times millions of a second. Blink and you'll miss it.
So here's the mystery. Even moving at almost the speed of light, a muon should only be able to travel about 600 meters before it just, poof, decays. But we detect them all the time, right here on the ground, after they've traveled tens of kilometers down through the atmosphere. How is that even possible?
And what's so wild is that relativity gives us two perfectly correct but totally different ways of looking at this.
From our point of view here on Earth, the muon is moving so fast that its internal clock slows way down because of time dilation. It stretches its lifespan long enough to make the journey. But now let's flip it. From the muon's perspective, it's just sitting still, and the whole atmosphere is rushing towards it. This causes the distance to the ground to actually shrink, an effect we call length contraction. So for the muon, it's just a short little trip. Two completely different explanations, but they lead to the exact same result. Amazing, right?
All right, so now we've got time dilation. We understand reference frames. We have everything we need. Let's go back to our twins and finally solve this thing.
So what's the solution? Well, it turns out the whole premise, that the twin situations are perfectly symmetrical, is just plain wrong. They're not the same at all. Sure, for parts of the trip, they see each other moving at a constant speed, but their overall journeys are totally different.
Think about the twin on Earth. They stay in one single, non-accelerating frame of reference for the whole 10 years. They're just chillin', coasting along with the Earth. No drama.
The traveling twin, though, their journey is way more complicated. They're in one inertial frame on the way out, but to come home, they have to hit the brakes, turn the ship around, and accelerate all the way back. That turnaround, that's not relative. That's a real physical event. You'd feel those G-forces pinning you to your seat, and that moment of acceleration is what breaks the symmetry completely.
And that is the key to the whole puzzle, that acceleration. It's an absolute event that unambiguously singles out the traveler. It forces them onto a completely different and, it turns out, shorter path through what we call space-time. The traveler on Earth travels in a straight line through time. The traveler takes a detour. And just like taking a scenic route on a map, their path has a different length. And that difference is the 4 years. So you see, there is no paradox at all, just the profound truth about how the universe works.
So, in the end, the twin paradox isn't a paradox at all. It's more like a gateway to understanding that time isn't some universal metronome ticking away for everyone at the same pace. It's a real dimension, woven together with space. And the path you take through this space-time literally determines how much time you experience. Which leaves us with a pretty deep question to chew on, doesn't it? In a universe where even the flow of time changes with your journey, what, if anything, is truly absolute?